Another special flavor of graph is what we call a bipartite graph. These show up very naturally in matching problems. What a bipartite graph is, again, we have a definition. I tend to not read these off directly. This is a graph that can be drawn in the following manner, where you have one set of vertices on the left and another set of vertices on the right, and edges only go from left to right. You can have a lot of edges that go from left to right, or some vertices that aren't connected at all to anything on the right, but there can be no edges between things on the left and no edges between things on the right. So red edges are not allowed. Not allowed. Determining if a graph is bipartite turns out to be easy in some sense, but I want you to try to discover how you could do that. It turns out we already have enough information to develop the theorem required to say a graph is bipartite if and only if something else is true. So I'll let you try to think about that and try to come up with that on your own. Similarly to how we had a complete graph, there is a complete bipartite graph, which is just as everything on the left is connected to everything on the right. So as our example, we're going to look at K43, which says we have 4 vertices on the left and 3 vertices on the right, and everything on the left is connected to everything on the right. So this first vertex is connected to those 3. The next one's connected to those 3. The next one is connected to those 3. The one on the bottom is connected to the other 3. So we have each of the vertices on the left has 3 edges. So the total number of edges is going to be 3 plus 3 plus 3 plus 3, which is also known as 4 times 3, which is 12. So the number of edges in K4, 3, or even better, m, n, is just m times n. Pretty neat. That's a nice quantity that we can now work with if we somehow need to compute this quantity. And again, this is sort of an upper bound on a bipartite graph. This is the biggest it could ever be in terms of number of edges.